we're going to look at Chapter 5. Down here. Might bring him back here in a minute, but right now. Probability. When we think of probability, or when I say the word, or you hear the word probability, what comes to mind?
There's a chance that something would occur or something would happen.
The chance that an event will occur. All right, so our objectives here, we're going to look at terms such as probability, experiment, event, and outcome. We're going to assign probabilities using a classical and empirical or subjective approach. And we are going to calculate probabilities using the rules of addition. We're also going to calculate probabilities using the rules of multiplication and using a contingency table. Finally, we will introduce you to Bayes' theorem and determine the number of outcomes using principles. A probability, a value between 0 and 1. Describing the relative possibility, chance, or likelihood that an event will occur. I want you to remember, it falls between 0 and 1. A probability of 0 indicates that it cannot happen. For instance, the probability our sun will disappear this year. A probability of 1 indicates that we're going to have chance of rain in Florida. Simply means for sure it's going to happen. As we balance this scale, a probability of 0 is like a coin toss. You have an equal chance of falling on either side. An experiment. Let's look at this example. So an experiment could be we roll a die. Let's focus on just discussion. A die. Have anybody ever heard that term?
Yep.
Okay, good English lesson here. Singular. Dice indicates more than one. So when you say you have a pair of dice. All right, so an experiment. You roll a die. What are the possible outcomes?
You have 6 of them?
You have 6 of them. You can roll the numbers 1 through 6. What are some of the possible events?
Even numbers observe a number greater than 4. You can observe an even number, you can observe a number greater than 4, or observe a number 3 or less.
Those are all events that can occur. All right, define. Let's go back and define these 3 terms. How would you define, how does the textbook define experiment?
A process that leads to the occurrence of one and only one of several possible results.
A process that leads to the occurrence of one and only one of several possible results. An outcome.
A particular result of an experiment.
The particular result of an experiment. And an event.
A collection of one or more outcomes of an experiment.
All right, recap. One die. I'm going to put all of his dots on one side. There's 6 dots on the dot. How would we define this? This becomes our experiment. The process that leads to the occurrence of one and only one of several possible results. What's the outcome? If I roll that die,
A result of what you get when you roll.
the result of when I roll. So it's going to be something between 1 and 6.
Mhm.
It can't be 1 and 2. So remember that definition. It can only be one outcome. And the event, how did we define that?
The collection of one or more outcomes.
The collection of one or more outcomes. So as I roll that, each time I roll, I'm going to get a different outcome.
Right.
But if I roll it 10 times, what are some of the events what are some of the outcomes I could collect?
Negatives.
Negatives.
Mm. Even numbers.
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 Odds.
Numbers greater than 4.
Numbers greater than 4. I might roll a
Yeah.
5 and a 6, or numbers greater than less than 3.
3, yeah.
You play that funny gambling, don't you?
I don't gamble, that's the problem.
If you're using negative, we better. If you're using negative dice, I don't want you to.
Right.
No, I do not gamble.
All right, so let's look at the complement rule. Someone tell me what this says.
Complement rule.
Mm-hmm.
Complement rule. Used to determine the probability of an event occurring by subtracting the probability of the event not occurring from 1.
Used to determine the probability of an event occurring by subtracting the possibility of an event not occurring. So what we want to say is that it's built on this premise. The probability of event A occurring would be equal to what? The probability
Of the event not occurring from 1.
All right, so look at it this way. All right, so here we're going to have our big circle. If we call that event A, and I'm part of a lot bigger board here, if this occurs, can this occur over here?
I don't know.
That's a no. So this would be that it does occur. This is the area in which it will not occur. All right, so let's look at it using some terms that we love. Remember what some of those terms we love in economics and statistics. What's it mean to be mutually exclusive?
Mutually exclusive means be it The occurrence of one event means that none of the other events can occur at the same time.
Correct. Now, in econ, you often hear that followed up with mutually exclusive and collectively exhaustive.
At least one of the events must occur when an experiment is conducted.
All right, so let's go and look at this. Let's assume that our experiment has two mutually exclusive outcomes. Based on the rules of probability, the sum of all outcomes must equal what?
The sum of all outcomes must equal.
What's our range?
1.
0 to 1.
0 to 1. 0 means
It cannot
Can't
happen.
happen.
likely, not expected.
Mhm.
We're not going to use more certain terms right now, but
Okay.
0 probably. We do not expect, under any circumstance, we do not expect it to occur. 1 indicates
Likely.
likely,
Very likely.
very likely. We do absolutely expect it to occur. The sum of all of our probabilities must equal, because if we do an experiment, we're going to have an outcome. So the sum of all of our probabilities must equal 1. All right, so if the probability of the first outcome, so we're going to say the sum of probabilities equals 1. And if I have, so I've got two probabilities. If the probability of event of 1 occurring is 0.61, what is the probability, using the complement rule, what is the probability of event 2? So the event that probability of 2 occurs is equal to 1 minus what?
0.61. What you have up there?
No, remember, I'm trying to define the probability of event of 1 occurring. The probability of the first outcome is 0.61.
Okay.
Okay. I'm using this little squiggly sign to indicate it's not going to happen. So we would say under this complement rule, the probability of outcome 2 occurring is equal to 1 minus the probability of event of outcome 2 not occurring. Let's solve for this. Now, what's the probability that outcome 2 will not occur?
What is the probability of the second one not to occur?
Yes.
Would that be?
You're getting ready to smack both yourselves on top of the head. This is so easy. Remember, the collection of all outcomes must equal 1. What's the probability? If this event occurs, can this event occur?
No.
Because they're mutually exclusive. So, the probability that outcome 2 does not occur, if outcome 1 occurs, 2 cannot occur. Remember, we're using this subtraction. So what's 1 minus 0.61?
0.39.
0.39. Now remember, to check yourself, sum that, and it should equal 1. Okay, 3 ways to assign probabilities. What's the first?
Classical?
The classical approach. What's that going to be based on?
The assumption that the outcomes of an experiment are equally likely.
Based on the assumption that all outcomes are equally likely to occur. What's the next one?
Empirical.
What do we mean by that?
Empirical or relative frequency is the second type. It's based on the number of times an event occurs as a proportion of a known number of trials.
The probability of an event occurring is based upon some fraction of the time that it occurred in the past. Okay, we're going to say that if this was the probability in the past, the likelihood that an event occurred in the past, whether or not it occurs in the future, is going to be based off of some fraction or it's going to be based on some derivative of that outcome. So we're going to say that if, an example, you came in. Okay, let's give a good example. Classical probability, give me an example. Well, before we do that, what's the third kind?
Subjective.
And subjective.
The likelihood of a particular event happening that is assigned by an individual based on whatever information is available.
All right, subjective, probably going to be the most difficult in practice because, again, we're going to have to use some human judgment here. We might not have anything from the past to go on, and we're just going to have to subject our reasoning based on whatever information we have available. So we said we had, what are the 3 ways?
Classical, empirical,
And subjective.
Okay. Classical is we're going to say these are equally likely. What's an example of classical probability?
They have the example of the 6-sided die.
6-sided die. So what's the probability of the event? Every time I roll that, I have an equal likelihood that any number can pop up. There's nothing going to favor any particular number. We know 1 through 6 have an equal likelihood. So how would I solve for this? If I were to ask what's the probability of rolling an even number?
So with those,
So
you have 3
You have 3 chances for
But you got
even or
2,
odd.
4, 6. So you have 3 chances of rolling an even number.
Number of favorable outcomes
Divided by the total number possible. So that would be 3 divided by 6.
So in that example of what's the probability of rolling an even, It could be 2, 4, 6. There's 6 total outcomes. So what's the probability?
0.5.
0.5. Empirical.
That one is the number of times an event occurs over the total number of observations.
All right, remember, likelihood that an event is going to occur is based off of some fraction of probability that it occurred in the past. We introduce a term here. The law of large numbers, which says that over a large number of trials, the empirical probability of an event occurring will reach its true probability. So the law of large numbers, what's the probability that, flip a quarter, what's the probability I land on heads?
50-50.
50-50.
Mm-hmm.
Would you bet every dollar in your checking account that if you had 2 flips that you would get a heads and a tails?
No.
How come?
That ain't no guarantee.
No
I'm gonna get
guarantee.
a head and a tail.
No guarantee. Well, you just said the probability was 50-50 though.
Yeah.
So therefore, if it was 50-50, it would mean that every time I flip it, I would alternate. We know it's not going to happen that way. The law of large numbers says, though, that if I increased the number of trials dramatically, so if I came out here and rather than just flipping twice, if I told you that you could flip it 10 million times, would you bet? I would.
I would.
The law of large numbers. As you increase the number of trials, as you increase the number of flips, you will gravitate and move more toward true probability. Yes, there's a 50-50 probability, 50% chance I'll land on heads. I may not do it back to back, but if I increase it 10, 20 million flips, you know, as I move further along and increase the number of trials, as I continue to increase it, I will ultimately reach, or I should expect to reach, true probability.
But there is still that chance that every time you flip, it'll land on tails every time.
We'll be dealing with empirical probability here. Empirical probability based on that science that it's going to be based off of that. And we do know if you increase, if you were going to do that experiment, you wouldn't come up and run that trial manually. Software would help you implement trials. Okay. In my world of investment research, we use some type of empirical probability. When I'm running simulations based off of some past occurrence, I'm trying to base the probability of a future outcome based on what I saw. And I can run a large number of trials in my research to see if I could move toward true probability. All right, let's look at another example. Does the book give you a space shuttle example?
Yeah.
All right, what do we have?
On February 2003, Space Shuttle Columbia exploded. It was the second disaster in 113 space missions for NASA. On the basis of this information, what is the probability that a future mission is successfully completed?
All right, so what's the probability of a successful flight? February 1st, 2003, Space Shuttle Columbia exploded. We know that it was the second disaster in 123 missions for NASA. On this, so we know they had 123 missions.
113. Ours,
100,
it says 113 in the book.
okay. So 113. My example here is showing 123. So on 113, and how many successful? That was just the second disaster.
111.
111 successful.
So we had 111 out of how many?
113.
It's 0.98.
What is it?
0.98.
0.98. See what we're doing? Subjective. The likelihood of a particular event occurring, this kind of sounds scary, based on an individual, based on whatever information is available. So remember, we have some human error here. We would find this when there is little or no data available to calculate probability using one of these two numbers. So we're going to have to arrive at it subjectively. What's some good examples?
I mean, in the doctor's office, they do subjective notes. So like a new patient comes in and they have to try and figure out what the patient's diagnosis are from just them observing all of the different things that are going on with that patient. But it's a subjective note because they have no previous notes or anything else from it. That's how we use it.
Okay, now assign this to probability. You're only good, just take that example and build it into a probability example.
So
You could say, what's the probability of a diagnosis of a particular illness
Yeah.
or disease based on, and that would be based upon these notes that I have.
mhm.
All right, sports fans. Just said you were a football viewer. We have football players in the room. All right, so who's your favorite team?
The Lions.
Detroit Lions. What's the probability that the Detroit Lions will win the Super Bowl?
It's very low.
But we don't know. We have no scientific
You're
evidence to go off of.
Right.
We have to take information that is available. We can take what's the schedule look like?
Right.
What's the roster look like? Are we injured? What's the schedule? Weather conditions. A lot of factors go into play, but it's just based on what information we have. There's nothing scientific about that. A fan would take that and analyze it and using your own subjectiveness, arrive at some probability. Estimating the likelihood that the U.S. budget deficit will be reduced by half in 10 years. Okay, now I would just take it where we came. This way, I would write down what I know. In the last year, we've added $1 trillion to our deficit.
Yeah.
So just based on that number alone, the information I have available would say there is a low probability. I would subjectively assign a low probability of coming up with all right, so to summarize, when we approach probability, we say there are two possible approaches we can follow. First, I'm going to say objectively assigning probabilities. If I objectively assign probabilities, I'm going to either use the classical, and that is based on the probability of an event occurring. All outcomes have an equal chance of occurring. My second objective approach is going to involve the empirical approach. this says, based upon the law of large numbers, the probability of an event occurring is based off of some fraction of the probability that it occurred in the past. Opposite of objectively. The third approach is I can come, if I'm not doing it objectively, I can come under subjectively. And this is the only approach here, and it is based on whatever information is available. Okay. Any questions? If not, let's move into addition. What are the rules involving the addition of probability?
Says there's two rules. One is the special rule of addition. We use the special rule of addition in events must be mutually exclusive.
We have the general rule of addition.
Okay, so remember we say that the outcomes are mutually exclusive. So we're going to add. So what's the probability that A or B occur? Okay, that's not right here. The probability of either A or B occurring is equal to the probability of A plus the probability of B. Now, let's assume. Do you have an example in the book about plastic bags?
Yep.
All right. Let's read this problem. Plastic bags with a mixture of beans, broccoli, and other vegetables. Most of the bags contain the correct weight, but because of the variation of size of the beans and other vegetables, a package might be underweight or overweight. And now remember, as a product person, we're putting this product out, and we base it off of that weight. We need to be fairly certain that if we're putting it on the grocery store shelf indicating a particular weight, we need to be hitting that weight. All right, so we're going to come out and we're going to sample 4,000 packages that were filled in the last month. And we say that, okay, so we've got beans, broccoli, and other vegetables. We'll just call it beans, broccoli, and vegetables. And we're going to survey 4,000. What's the probability, the book gives us, what's the probability of either A or C occurring?
A is 0.025. C is 0.075.
So what is the probability? Let's say, what's the probability that A or C occur? And probability A, we would say, would be underweight. What's B, equal?
Yeah, B, satisfactory, equal, yeah.
And C is
Overweight.
overweight. Okay, so what's the probability that we're under or overweight?
0.10.
0.10. Now, using this complement rule, what's the probability that we would be at equal weight?
.90.
0.90. And these two together better sum to 1. So remember, using the complement rule, we would say the probability of B occurring is equal to minus the probability that it doesn't occur. 1 minus the probability it doesn't occur. Well, we know since it's mutually exclusive, the probability of A or C is 0.1. 1, so if A or C occur, B cannot. So the probability B occurs is 1 minus 0.10 or 0.9. Now what's this general rule probability?
The outcomes of an experiment may not be mutually exclusive.
So here under the special rule, we are deciding that it is, here's this term, mutually exclusive. And under this general rule, we'll say it may not be mutually exclusive. So in this example, let's say that I have 3 possible outcomes. We're going to call this one A, we're going to call this one B, and that one C. And in this area, I want to highlight, this is what's going to distinguish that they're not mutually exclusive. Before I put C up there, I had 2 possible outcomes. Those were mutually exclusive. Now I put C up here and I have this overlap. Because of that overlap, I see it is not mutually exclusive. We define this area here, these 2 areas, as a joint probability. All right, so how are we going to solve for this? Well, let's look. What do we call this, by the way? What kind of diagram?
Venn diagram,
We have the
VENN.
All right, so the Venn diagram. Well, let's say 200 tourists. You have this example in your book?
Mm-hmm.
Yes.
All right, we're going to look at Disney World Busch Gardens. We're going to do a survey of 200 tourists who visited Florida during the last year. The results showed that 120 went to Disney World, 100 went to Busch Gardens, and 60 went to both. So let's define this as Disney. And we're going to define this as Busch.
Mhm.
And then this is the joint probability that you went to both Walt Disney World and Busch Gardens. So what is the probability that we went to Disney or Busch?
So when they surveyed 200 people.
200, and I know that 120 went to Disney.
Right.
What's that probability?
60.
60%, so 0.60.
How many went to Busch?
50.50.
0.50.
So 50 go here,
Mhm.
50 or 0.5. And how many visited both? How many went to both?
I mean, he went to both as in add them together.
How many both went? What's the problem tell us?
120 went to Disney, 100 went to Busch.
And how many visited both?
It doesn't tell us on here. Both was 0.30.
So 0.30. Now right away, 0.6, 0.3, and 0.5, does that equal 1?
No.
No. So what are we going to have to do? So the probability that you went to Disney or Busch is going to be equal to what? The probability of Disney
Should be equal to 1.1.
equal to the probability of Busch. Subtract out what?
Oh, the 30 in that went to both.
The probability of both.
So it should be 80.8.
So the probability of Disney was what? 0.6.
0.6.
Plus 0.5.
Probability 0.5.
0.5.
Minus 0.3. Plus 0.8.
0.8. So what we are doing is we're subtracting out,
The probability of
We're-
somebody won the both.
we're subtracting out that joint probability. All right, any questions over this?
No.
I think you'll find probability to be one of the easier components. If you advance your studies in statistics, you'll find where you're taking classes. I'm recalling my own undergraduate career of taking an entire 16-week course on just probability. And I can say of my own subject matter, I find probability to be one of the more interesting concepts. All right, multiplication. So what's our special rule? Let's start with this. Special rule of multiplication says what?
Requires that two events, A and B, are independent.
Requires that they be independent. And remember, they are independent if the occurrence of one has no effect on the occurrence of the other. So we have two independent variables. And we could say that this is written as what? The probability of A the probability of A and B is equal to what?
Probability of A times the probability of B.
The probability of A multiplied by the probability of B. All right, let's say, work with AAA. AAA reveals that 60% of its members made airline reservations last year. AAA, 60% made airline reservations last year. Two members are selected at random. Keyword being random. That's going to imply independent. Two members are selected at random. Since the number of AAA members is very large, we can assume, okay, we're going to assume that the two that we pull are independent. And again, if I saw the word selected at random, I would think there's no bias present. All right, so the probability that the first member made an airline reservation last year is what?
0.60 to 60%.
So the probability of the first reservation is equal to 0.6. And what's the probability that their second reservation was made online? 0.6. So what's the probability that both reservations were made online?
0.36.
So the probability of R1 and R2 is equal to the probability of the first one times the probability of the second one, which equals okay. Here we have, just like with addition, we have the special rule. What's the general rule imply? Let's carry this out like this.
The general rule is if two events are not independent, they are referred to as dependent.
Well, if you're not independent, you are dependent. Okay, so the general rule used to find when the joint probability are not independent. Okay, it states that for two events, A and B, the joint probability of both events will happen is found by multiplying the probability that A will happen by this. Let's introduce this term, the conditional probability that B will occur given that A has occurred. So here's how we write this. The probability of A and B is equal to what? The probability that A has occurred multiply the probability. So B is only going to occur if A has occurred. That's what this, I'm not dividing. That's why I'm just drawing that line down to let you know. B will only occur given that A has occurred. So we have this conditional probability. Conditional probability. The probability of a particular event occurring given that another event has already occurred. All right, let's look at an example. A golfer has 12 shirts. Suppose that 9 are white. I'm a UK player, University of Kentucky. 9 are white. Let's give the others blue. So how many are blue?
3.
3 are blue. He gets dressed in the dark. This is me every morning. I come out, I'm dressing in the dark. I reach in my closet and I've got 12 shirts hanging up. 9 are white, 3 are blue. And I just reach in there and I grab a shirt out. What's the likelihood that I draw a white shirt? So the probability of a white shirt is what?
That'd be 9 divided by 12.
Is equal to?
.75.
Okay. Now, next day comes around and I don't do laundry. Again, I'm in the dark. I reach in and I pull a shirt out. What's the probability that I draw a second white shirt?
9 divided by 11?
No, 8 divided by 11.
8.
8
That's right, 8 divided by 11.
And that is the conditional piece of it. Right here, I started with 9. I drew white the first time, so I couldn't have drawn that white again.
Yep.
All right, now, let's divide this out.
So then you would multiply those two together?
Well, first I'm asking to divide here.
Oh, it's 0.73.
Yeah.
All right, let's start this. Now, we're going to apply the general multiplication rule. And that says what? The probability of what? A and B is equal to what? the probability of A, finish this for me.
Times probability of A, of B, A. B, A.
So again, the probability of A and B occurring is equal to the probability of A multiplied the probability of B, given that A has already occurred. So the joint probability of selecting 2 white shirts is equal to the probability of A. First white shirt was 9 out of 12. And the probability of pulling this second white shirt, given that we already drew the white shirt up here, 8 over 11. What do we have here? We didn't need to take this out right here.
0.55.
Okay. Contingency tables, let's get through this. Are we good with addition and multiplication?
Yes.
All right, let's just define a contingency table and base theorem.
A table used to classify sample observations according to 2 or more identifiable categories or classes.
Table used to classify sample observations according to 2 or more. Here's an example. 150 adults are surveyed about their attendance of movies during the past 12 months. The respondent is classified according to 2 criteria: number of movies attended and gender. So we could say that, you see this in the book?
Mm-hmm.
Okay. Based on the survey, what's the probability that a person attended 0 movies? So at 0 movies, we see that there were 20 men
41.
and 40 women.
So it'd be 60.
So it would be 60 divided by what? What was the total sample size?
150.
150. So 60 divided by 150 would be the probability that 0 movies were attended.
Point
4.
0.4. All right, now tree diagram. I find a tree diagram to be very helpful when it comes to planning. So this is a useful tool for portraying conditional and joint probabilities. Particularly useful for analyzing business decisions involving several stage areas. It can be used as a graph and it's helpful for organizing calculations. Okay, now each segment of the tree is one stage of the problem. And the branches of a tree are weighted by, now just picture a tree, the branches of the tree are weighted by the probability that they could occur. Okay, a tree diagram. Sample of executives. What are we given here? Sample of executives were surveyed about their loyalty to their company. One of the questions was, if you were given an offer by another company equal to or slightly better than your present position, would you remain with the company or take the other position?
Which one are you on?
The responses of the 200 executives were cross-classified with the length of the service to their company. Are you giving an example of the?
This is the one for the movies, from the previous one.
Okay, so we used the example of the movies.
That's what this tree diagram is.
Okay, and I used the movies for?
It was for the
Facebook.
contingency table.
Contingency table. Okay, so let's look at okay, so here we go. A sample of executives surveyed about their loyalty to their company. If you were given, so here we go, we just read that. So less than 1 year, so we're looking at loyalty based on length of service. All right, so less than 1 year, 10 are saying that they would remain. 25 are saying they would not remain. From 1 to 5 years of service, 30 will remain, 15 will not. 6 to 10, 5 would remain. So we're going to say less than 1 year. And 1 to 5 years. 6 to 10 years. Greater than 10 in the total. Okay, so would and would not. So less than 1 year, 10 and 25. Let me populate this real quick. 30 and 15.
5 and 10, 75 and 30.
75 and 30.
Yeah.
And our total?
Is 120 and 80.
120 and 80. Okay. So here we have 35, 45, 15, 105, 200. All right, you with me?
Yep.
All right. Now just put this data up on the board. And let's build this tree diagram. So, starting out, we're going to have one starting point. What are the two possible outcomes? You're either going to remain
Or not.
and what's the probability that you would remain? Is 120 over 200. And this is 80 over 200. Now, of this 120 that would remain, what are my branches now?
Less than 1 year would be 10.
Well, remember, if I'm going to remain, so would,
Uh-huh.
I would have 10 over 120. Okay, my over 10 year is 75 over 120. So this is the less than 1 year. Now, would not remain. We have the same outcomes.
It'd be over 200, wouldn't it? Would it be under 200, over 200?
No, because of my remain, remember, our total is 80.
Oh, okay. Okay.
Now, what's the probability that I would remain is less than 1 year?
Yeah.
So let's use some multiplication rules. $120 over 80 multiplied by what?
This is what, less than 1 year?
Yeah.
Okay. So is this another part of our tree?
This is our tree. This is our tree right here.
Okay.
I'm going to show you how we check this tree real quick.
Oh, okay.
So what's 10 divided by 120? 0.06. If you solve each one of these out real quick, let's do that. What's here? 1 to 5 year. Oh, 120 over 200. Is that what you said?
Yeah, that's what.
Because you're taking the total probability that it would occur multiplied by the probability of that one branch.
Yeah, okay.
So here, you're still at 120 over 200 multiplied by, what's the probability of that one branch? 30 divided by 120 is equal to 0.15. 6 to 10 year. Still, total probability 120 over 200 multiplied by
5 over 120.
5 over 120. What's that give me? 0.025. And finally, greater than 10 years. 120 over 200 multiplied by
75 over 120.
75 over 120 gives me what? For the sake of time, 0.375. Doing this on out. you would sum the rest of those out, and my sum is going to be equal to 1. So there we go.
I think that top one was supposed to be 0.05 because it's 1.01.
Point the top one is.
Yeah.
A lot of times I rely on you all to do the math.
Yeah, no.
All right, here we go. Lastly, Bayes' theorem. A method for revising a probability given additional information. Computed using this formula. The probability of event B occurring given that A has occurred. We're out of time, but rely on Bayes' theorem here. Make sure you look at this video. All right, in closing, probability. Again, why do we go back and take samples? Remember, we're using it to tell us something about the population. We each looked at examples here of how probability could be used in business. From the surveying of weights of vegetable bags to the probability of space shuttle launches. Now, those are two completely opposite as far as the weighting of how, let's just say, we should care more and put more close emphasis on space shuttle launches than whether or not we're off by a couple of ounces. Use that in your thinking this week. When dealing with life or death matters, or matters of high, this is going to set the stage for future. Okay, life or death matters are setting the stage for more relevant or more pertinent outcomes. Again, life or death, surgeries.
Mm-hmm.
Think about, you want higher probabilities of knowing. If you're sampling and you're using data and you're using probability analysis, you want to have a higher probability of important events occurring or not occurring. If they can carry less weight, even if they occur, so what? We might assign lower probability rules or lower probability understanding within our own organizations. So, again, hope you found it hopeful. Hope you found it beneficial. I will see you next week.